speeds and quick maneuvers of aircraft and missiles create stresses and strains that are supported by structural components made predominantly of aluminum alloys. Because of favorable strength-to-weight ratios and ease of machining, millions of pounds of aluminum are used each year to fabricate parts of various sizes and shapes. As parts become larger, so do the machines on which they are fabricated. Milling machines with beds 100 feet long and 20 feet wide can be found in numerous factories throughout the United States and other countries. Each part starts out as a forging or a slab of aluminum plate. When parts are too large for a forging, they must be machined from plate stock. With the introduction of numerical control combined with the versatility of the computer, major strides have been made in the speed and accuracy of machining components. Increased speed means that aluminum chips are produced at a faster rate. Each year, millions of pounds of chips are processed as scrap and add significantly to material costs. Machine parts made from aluminum plate can often result in as much as 90% chips. Fabricating parts without creating chips would save millions of dollars in material and labor annually. A new technology has shown that this part, weighing 0.95 pounds, requires a preform weighing only 1.06 pounds, or 3.8% scrap, whereas 5.12 pounds of material is required for machining, resulting in 81.4% scrap. Introducing this new technology, FlowForge. Here's how the FlowForge process works. An aluminum blank is inserted in a FlowForge forming die. The female portion of the die is machined in one piece to the exact dimension of a finished part. A steel cover plate is placed over the aluminum blank. The male portion of the die is divided into segments where each segment can move independently of each other. The concept of FlowForge is to force each of the male segments down into the die cavity, thus shaping the material to conform within the female die. When all of the male segments are in position, they are secured by a locking wedge so that each segment maintains a vertical position as it moves down. The die assembly is then placed in a furnace and heated to a predetermined temperature. Aluminum alloys, lithium aluminum, and metal matrix composites are formed at a temperature of 850 degrees Fahrenheit. Platen adjustment is made prior to pulling the die assembly past the inclined surface. Platen positioning determines finished part dimensions and can be easily and accurately controlled. Upon reaching the desired temperature, the die assembly is moved from the furnace and secured to the piston of the hydraulic cylinder. As the male segments come in contact with the inclined surface, each segment is gradually forced down, shaping the heated aluminum to conform with the die cavity. This process is rapid when compared to machining. The die is pulled by a hydraulic cylinder past the inclined surface at a rate of 1 foot per minute. This experimental part, which is 11 inches long, requires approximately 1 minute to FlowForge. This machine part, 10 feet long, required 20 hours of machining and 4 hours of hand finishing. If processed in a production FlowForge system, it is estimated that 5 hours would be required, the actual FlowForge time being only 30 minutes. After the forming process, the male segments are extracted from the female by an extraction ramp. When all of the segments are securely on the elevator platform, they are raised and the female die is returned to the starting position. The female die is then removed from the die holder and placed in the ejection station. Hydraulic pressure is used to eject the finished part. The black coating on the part is the high-temperature forming lubricant required to reduce friction between the aluminum being formed and the steel die surface. The small amount of flash created by this new forming process is removed with portable tools, and any hand finishing is significantly less than that required on machine parts. After removal of flash and surface lubricant, the finished part is net shape and has an RMS 32 surface finish with no machine marks. Cutter marks on machine parts require hand finishing, and if not properly performed, can contribute to premature component failure. Minimizing the use and maintenance of cutters, along with the expense and control of lubrication and cooling fluids, would lower costs and increase productivity. The material required to make this part, with rib height to thickness ratios greater than 10, is about 20% of the material usually required for machining. A double-flanged part with varying thickness and tapered sides can be formed with very little scrap, similar to a part with flanges and ribs on one side. As a part of the same length becomes more complex in detail and configuration, the FlowForge processing time does not change. When compared to conventional forging, FlowForge is a significant move toward automation and improved reproducibility. FlowForge dies do not have to be as large and bulky as conventional forging dies. The load-carrying die holder can be a weldment rather than machined from large billets. FlowForge forming pressure is localized and occurs only within the platen area. Dies can be designed with less bulk because they are captive within the die holder. Many FlowForge dies within a prescribed size category can use the same die holder. Because of the progressive forming action of the FlowForge process, net shape parts can be produced much larger than the limit of conventional forging equipment. The design and fabrication of a production FlowForge system is many times less costly than conventional forging presses, which have multiple large diameter hydraulic cylinders and accumulating tanks supported by remotely located high horsepower pumping stations. A proposed small FlowForge production system designed to make parts 20 inches wide by 100 inches long using only one medium-sized hydraulic cylinder would be capable of making net shape parts not possible with existing 50,000-ton presses. For many years, the Air Force recognized the need for larger, more efficient forgings. They solicited the forging industry and proposed a 200,000-ton press. The high cost of $500 million was a decisive deterrent, and the project was difficult to achieve concurrence. The doubtful engineering and construction feasibility were also major deterrents. Both of these deterrents no longer exist with the introduction and development of the FlowForge system. The Lowy press with a 70-foot deep foundation and the Mesta press with its bank of accumulating tanks are extremely large pieces of equipment with high operating costs. A FlowForge system approximately 12 feet high will rest on a footing rather than be submerged in a foundation. Its design, construction, and operating cost is estimated at less than 5% of the 200,000-ton press. One of the significant attributes of the FlowForge system is the potential of making long net-shaped parts not possible with conventional forging equipment. A production FlowForge system will not only make possible the net-shaped forming of large aerospace components, it can open the door in other industries where large structural aluminum panels can be efficiently used to replace other materials. The magnetic levitation train can be designed with a one-piece aluminum FlowForge part as its base structure. Civil engineers can utilize a new dimension for using sculptured aluminum panels that are structural as well as ornamental. Bridges, which have been predominantly made of steel, are becoming an expensive maintenance problem. Large aluminum structures could revolutionize the bridge building industry. Another future transportation application is in building tunnels for above and below ground. Large aluminum FlowForge panels would lower costs and reduce construction time. High technology projects, such as the tunnel for the Super Collider Corridor, are also another consideration. Engineering periodicals have published that 26 million tons of metal chips are produced annually. Aluminum chips, which contribute significantly to this total, will be reduced when FlowForge technology is available to industry. The FlowForge team that developed this new technology has demonstrated the feasibility of fabricating parts without making chips. Future savings in material and labor will be realized when FlowForge is in production, moving not removing metal.